afternoon, everyone. I'd like to thank the organizers for the introduction and for having me here. So, my name is Remy Notermans. I'm with Atom Computing, and today I'd like to talk to you about our neutral atom platform and the progress we've made so far and where we're headed to as a company. So, let's see if I can get started on the slides. Perfect. So, this is a brief overview of Atom Computing. The company was founded 5 years ago in 2018. I joined not long thereafter, so we're just with a few people. And in the meantime, the company has grown to over 60 employees. Over 2/3 of those people have a PhD in physics, because we just really need that experienced team to build this cutting-edge technology. And we're building quantum computers based on atomic arrays of neutral atoms. We're building these atomic arrays because they provide a highly scalable approach to get to the qubit numbers that most people think we need in order to reach the fault-tolerant regime. We initially built a 100-qubit prototype in Berkeley in California, and we recently expanded into Boulder, Colorado, have a new facility there where we're building our next generation systems that are going to be commercially available once they're up and running. And we'll primarily provide the cloud-based quantum computing as a service. But we're also exploring opportunities to actually sell some of our systems for on-site, on-premise applications. So, we are a hardware-focused company. We're not full stack. We really believe that we're building the tool, and we want to partner up and collaborate with partners to explore the opportunities and the use cases that I think most people agree on are going to touch many, many industries in various ways. And I've set into some of the panel discussions where there is a lot of active work going on in exploring these use case scenarios, and this is exactly the conversation that we also want to engage in as a hardware-focused company. So our mission as a company is to build large-scale, fault-tolerant, universal gate-based quantum computers. And the reason why it's such a precise description of our mission is because a lot of these statements require us to achieve very particular technical goals that we're really focused on solving and building to scale. So I would like to give a short overview and introduction of how a neutral atom quantum computer generally works, and sort of show it here schematically. So we use optical tweezers, and an optical tweezer is nothing else than a laser beam that gets focused down into a tiny, tiny spot. And if you choose the wavelength or the color of your laser beam appropriately, then an atom wants to stay in that focal point of your laser beam. And so it acts like a tweezer. If the atom is in the tweezer and you move the laser beam around, the atom will follow, so you can suspend your atoms in a vacuum chamber. The nice thing is, once you have it suspended in your vacuum chamber, you can use another laser beam to actually turn the atom into a qubit and perform qubit rotations. In a similar way, when you have two atoms or qubits next to each other, you can use a laser beam that acts on both atoms at the same time and actually entangles them through some long-range interaction that we call the Rydberg interaction. So essentially, just with laser beams, we can induce single qubit and 2-qubit operations. Of course, we don't just have 2 qubits. We make atomic arrays, so an entire array of focused laser beams of optical tweezers, and in this example holds 100 qubits in a 10 by 10 array. The nice thing about this technology is that it's relatively straightforward to just increase the qubit number in 2 dimensions, or even beyond that. And the other thing is that they're atoms. They're very small, they're neutral, so they can be really close together. And so actually in a vacuum chamber, this entire array is like the width of a hair. So it's tiny, tiny volume that you can contain your qubits in. So in real life, in a real world setting, you have this vacuum chamber. It's in a room with a lot of optical components around it. They're all boxed in. But that's really all you need to build this platform. And the nice thing about this is as we increase the number of qubits in this vacuum chamber, we can scale by many, many orders of magnitude, but the footprint of the entire system stays the same. It will still fit in a single room. And so this scaling roadmap sort of shows that not only do we scale in 2 dimensions, we go to a 3rd dimension to really leverage the cubic scaling of this system. So apart from the scaling in qubit numbers, one of the really nice thing about our particular qubit is that it's a nuclear spin qubit. And a nuclear spin qubit is created by the essentially the spin of the nucleus of the atom. So if you imagine the atom being a nucleus with a cloud of electrons around it, instead of manipulating the electrons of the atom, you're just manipulating the nucleus of the atom to either point up or down. And those are your 2 qubit states. The advantage of that is that it's a very well isolated system, so it's quite insensitive to environmental noise. So just by the fact that Mother Nature gives you that kind of shielding, we have industry-leading coherence times on these nuclear spin qubits that go into like the tenths of seconds. So you can start and create a superposition with these qubits, walk away, talk to somebody and come back, and they're still coherent with each other without doing any dynamic decoupling or spin echo, any other tricks. The reason that's nice is because it provides you this massive natural overhead to do these other more complicated operations like error correction or run deep circuits or explore hybrid computing opportunities. And we don't have to fight these timescales that are in the millisecond or in the microsecond range. We just have tens of seconds and a lot of overhead. A new development that we have in our 2nd generation systems, and we recently posted this on arXiv, is the capability to perform mid-circuit measurement, which is one of the pillars to build a fault-tolerant quantum computer system. So the way we do this with atoms is sort of schematically shown on the right, where we have a small array of 9 qubits. And in the first step, we choose, in this case, 2 qubits that we would like to read out. So the one in the bottom right and the upper row in the center. All the other qubits with an auxiliary laser beam will be pushed out of resonance for the imaging transition. The advantage of that is that we're not actually changing the qubit states, we're just moving them around without really changing the coherence of the system. So once those other qubits have been shifted away from resonance, they've been turned dark, we can read out the 2 qubits that we're interested in. By virtue of the way that we read out the qubits, they automatically get reset into the 0 state. And so at the end, in step 4, we turn off all the lasers, we've read out the 2 qubits of interest, and they're being reset. So, and the qubits stay in the tweezer. So we have qubit reset and reuse in a few simple steps without changing or affecting the coherence of the other qubits. So in the arXiv paper, there are more technical details, but one of the biggest things was really that we can do this, we can employ this technique without impacting the fidelity and the readout error of our qubits. In fact, actually, it turned out that our spam fidelities were really good, and that gives us a lot of confidence that we can employ this at scale in our 2nd generation systems. So some of the things that I mentioned, like the long coherence times and like the mid-circuit measurement, technique, we can do all of that quite effectively because we're leveraging the natural advantages of using neutral atoms. So when you use atoms of a single isotope, you don't get any fabrication imperfections because each atom is identical. We get the long coherence times. We locally do wireless control because we're using lasers in free space. That doesn't mean that there aren't any 19-inch racks around the system that do have cables, but locally, where the qubits are, there is no wiring. There are no sources of noise. There's just light. And we can control that light very, very well. Our platform allows to exponentially scale the number of qubits by many, many orders of magnitude, while maintaining the footprint relatively compact. And we're able to do this because we're just leveraging a lot of the scientific advances of the last few decades that now are technologically just readily available. And to sort of drive home that point a little bit more, I just listed a few of the Nobel Prizes that have been awarded in the last 2-3 decades that all, at the time, were groundbreaking results, like laser cooling and trapping of atoms, high-precision optical spectroscopy, the ability to manipulate quantum systems, optical tweezers, and even last year, the entanglement experiments that showed that entanglement is a real effect that we can leverage. For instance, with laser cooling and trapping was groundbreaking in the 90s, and at this point, we know it works. So as an engineer, you design your system with the right wavelengths, with the right optics, with the right magnetic fields. You put it all together, you flip a switch, and you have a cloud of cold atoms. This is not research anymore. And we're really leveraging that kind of knowledge to build these systems at a very high pace. Another particular thing that we do at Atom Computing is we build our own control systems, hardware and firmware. So we have our own control systems team of electrical engineers and FPGA engineers that design and build our own RF, microwave, and digital control systems, integrate them, write the firmware, and this is what we're actually just integrating into our systems. The very big advantage of that is the incredibly fast turnaround time in feature requests, bug fixes, etc. And it also allows us to really design our control systems in a way that we can scale to these many, many orders of magnitude increased number of qubits. It just gives us a lot of velocity in order to build these large systems. So where are we at as a company? We built a prototype system, a 100-qubit system in Berkeley in California to sort of prove the nucleus spin qubit principle and the complete system functionality. And right now we're building 2 commercial systems in Boulder, Colorado, where we really are scaling the technology and also making some technological improvements and systems integration improvements to improve the performance, the quality, and the reliability of the systems so that they will be ready for commercial deployment. So as I said earlier, we are a hardware-focused company, and because of that, we are really open to engage and explore with multiple parties for various kinds of opportunities, such as research collaborations, optimized algorithm development. Maybe there are companies who are trying to figure out how their use case will work on our platform. How do we work and develop algorithms that can work in a hybrid environment? And of course, the on-premise systems that I mentioned earlier. For the research collaborations, one of the examples I can give you was actually announced earlier this week, where we work with the National Renewable Energy Laboratory in the United States and help them for the first time to actually integrate quantum computing into their processes to investigate how they can employ quantum computing to improve their decision-making processes when there are, for instance, electrical outages or failures. So this is really from the bottom up, a sort of use case exploration of like, well, at NREL, at the research facility, they've never really integrated quantum computing. They don't have the know-how, but working together with us, they've started building up a foundation on understanding how quantum computing works, how algorithms can work, and how they can be integrated in order to help them improve future processes and decision-making processes. So that's actually the final note that I would like to leave this on, which is that we are very much open to talk to you about ways that we can collaborate. So I would like to thank you for your attention.